Welcome to Group 18's analysis of a left crank arm. Today we are analyzing and optimizing the left crank arm of a mountain bike using static mechanics principles. Mountain biking subjects crank to extreme loads up to twice the rider's body weight and sudden torque spikes during off-road use. Our goal is to identify critical stresses and propose lightweight, durable design solutions. Let's start with the key assumptions. Geometry: a 170mm long crank arm with 25mm diameter, a peak pedal force of 710 newtons. Material: aluminum alloy. Under these conditions, we analyze 4 stress types: axial stress, bending stress, torsional stress, transverse stress. Our results show that bending stress dominates at critical angles like 90 degrees with a maximum von Mises stress of 440 MPa.
Hello, my name is Abatakarin Kwachirama and I'm going to present sections under loading scenarios, stress analysis, and combined stress evaluation. Under our loading scenarios, we have our free body diagrams representing our crank arm at different angles and our force applied at different angles. And for our presentation, we're going to use the free body diagrams at 0 degrees. To get our internal forces and moments, we sanctioned our crank arm at 170 millimeters. At 0 degrees, we have our F of Y, which is our shear force, our moment about x-axis, which is our torsion, and our moment about z-axis, which is our bending moment. And the graph on the right represents our maximum force that the crank arm can accommodate before it breaks. And going to our next section, which is stress analysis, we have analyzed 4 stresses: our axial caused by the normal force, bending caused by the bending moment, torsion shear caused by the torsion, and the transverse shear caused by our shear force. And the graph on the right represents all the stresses at different angles. And our next session, combined stress evaluations, it shows our superposition of normal stresses and shear stresses. The graph on the right shows that our normal stresses are the dominant stresses throughout all the angles that we have analyzed.
Good day. My name is Nkoslenhle Dlamini, and I'll be taking you through the critical combined stress state and the stress distribution across the cross-section. The analysis reveals that the crank arm is subjected to a combined loading condition primarily involving bending stress, torsional stress, and transverse shear. Upon calculation, we discovered that the principal stress is approximately 115 megapascals, and it occurs at the outer surface near the crank root. This is also revealed by a simulation we conducted. The greatest individual stresses occur at the crank root and the pedal hole. The crank root experiences the maximum bending moment, making it the point of highest bending stress, while the pedal hole experiences torsional shear stress due to the applied torque. At the critical location near the pedal holes, the crank arm experiences peak stress at the outer surface due to the combined bending and torsion. Bending stress varies linearly across the section, while torsional shear is highest at the outer edge. The pedal hole introduces stress concentrations, making this region most vulnerable. Therefore, a hollow elliptical cross-section effectively resists both types of stress while minimizing the weight. We made use of a plane stress element and a volume stress element to further visualize these findings.
Good morning, my name is Kenyanga Mukonda. Design recommendation and material selection. Based on our stress analysis, we recommend a hollow elliptical cross-section with a major axis orientated vertically. This shape increases the secondary moment of area in the direction of bending, significantly improving the resistance to bending stress without adding unnecessary weight. Because it is a closed shape, it also maintains a strong torsional stiffness, and its smooth curves reduce the stress concentration that typically leads to fatigue failure. For the material, we recommend aluminium. It offers a high yield strength of approximately 500 megapascals, a good fatigue resistance, while also being lightweight and cost efficient. Compared to steel, which is heavier, titanium, which is more expensive, aluminium provides the best balance between strength, weight, and manufacturability. However, due to aluminium's low stiffness, we compensate by increasing the moment of inertia, which is easily achieved using the elliptical cross-section. This combination mirrors what is used in many high-performance crank arms and ensures safety, reliability, and efficient design for mountain bike application.
In conclusion, my group members and I identified bending stress at 90 degrees under the 710 newtons pedal load as the most critical case by adopting a hollow I-beam cross-section and adding smooth fillets at concentration points. We increased the section modulus without extra mass, significantly improving the fatigue resistance. Moving forward, we will integrate dynamic loading cycles and detailed fatigue life analysis to fully validate and refine those design enhancements. Thank you.